Howdy, everybody. Hope you're doing well wherever, whenever you are. We are here for Quest 19, Everybody Codes 2025. We're almost done. The this one was from Thursday. I'm recording it the day after, so I don't think my actual times will be very good. I do think my personal times will be okay, and so just to give a heads up for the times, they're gonna look off whack, but it's mostly because I had a lot of time to think about it. Like where I went for Thanksgiving for my holidays was about an hour drive, so I had a lot of time to kind of think about it as I was solving it. And I had looked at it on my phone, and but I wasn't logged in, and so I don't think my times will be accurate to how much actual processing power it took, because it did take a little bit of time. Anyway, we'll discuss it. This one's also a little crazy because the solution that I had that I came up with in the end actually works for all three parts. So I'm inclined to do this a little bit differently. I think briefly I'll describe the problems for part 1, part 2, and part 3, and then just in part 3 I'll have the actual code review and show you what's happening, because it's literally the same thing for all three parts. So I think that's how today will go. Again, I've loved doing Everybody Codes. It's been a lot of fun, and it's been fun seeing all of your solutions. I haven't looked at solutions for Quest 19, or I just finished Quest 20. I tried to do it right as it opened, or close to when it opened, so that I could kind of, get a decent time, I guess, to see how well I did. That one did take me a few hours, I think. So I'm recording this after, but we'll still go through this. I haven't looked at my duck either, so I don't know what it looks like. So the Reddit and everything will also be a surprise. So with that, let's just get into it. Okay, so what's happening? You're playing Flappy Birds, if you remember it. And that's the quest name, right? Flappy Quack. We're flapping. The idea is you've sensed your way through a large tunnel system, and there's walls within the tunnel, and each of the walls have gaps, and then the walls are separated. And the gist of what it wants you to do is, what are the minimum number of flaps? So when you flap, you go up. When you don't flap, you go down. What are the minimum number of flaps to go up and down, or to minimum number of flaps, meaning to go up, that you need to get to the end? And so they give you a pretty good example. So they're given this input, it would look like this, right? So it's 5 positions away. It starts at 3 positions up, and the gap is 4. So 5, 3, 4 that's what that means. And so they're going to give you a list of them. You're going to draw a grid, and it's going to end up looking like this. And so you're going to start here, and so you have to find what's a valid way to get through flapping. And so then they actually give you an example here, right? It's this is a valid one. You flap up, go down, 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 then you go up here, then you go down, then up, and then down, and here. Now you've reached it. So this is this is actually just one of them. I think because you could go one more up here, and then the rest of your thing would be like this. And then, again, you could do this, and that would be valid too. This is all just to say is there's some number of flaps that you could do that would be, there's different paths you could take that would be valid, but there's definitely paths that are invalid. If you flap too high up here, then when you're falling, you're going to hit a wall, because you move one step every, if you think about every second, the thing's moving forward. And if you flap up, it takes you up a position. If you don't do anything, it takes you down a position. So there's kind of a limit to how high you can go and how low you can go over the time. And that was one of the key things that helped me solve the puzzle, which we'll talk about later. What changes in part 2 and part 3 is they now say there's multiple gaps, right? So here in part 2, they say you may get multiple gaps. So at the 7th rank, there's 2 gaps in that thing from 1 to 3 and or sorry 1 4 3 7 4 2. So you can see now this one has a new set of gaps, and the ending has 2 new sets of gaps. So now, because that gapping is changed, you can kind of like do a simpler flight here and then kind of here and then down here, right? So you can see here you can do this, and now you get, it turns out the net effect of going here and down here is the same as like going here and just going up and down and then going up and then da 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 and then down here, right? But the new minimum is 22. And then part 3, the only thing that changes is it's just a much larger scale. So you can see the distances are huge, ginormous. And I'm glad I kind of had time to think about it and figure it out, because like here in part 3, the sizes are so big that it just becomes unfeasible to do like Dijkstra's, which is what I was thinking of doing. Admittedly, so like if you look at the numbers for part 3, like these gaps are like not super big, but they're still really big, right? And so your ability to like do like a shortest path thing with like Dijkstra becomes much harder. In part 1 or 2, my initial thinking was, when I was looking at part 1 and when I was thinking about it in my head, was, oh, I could just do Dijkstra. And like the way that I was imagining it is all of the points in the gap are like potential ones, but they're only valid if I can get there from a position that I was previously. So your like quote unquote neighbors function would be asking yourself the question, can I actually get to this point, right? So this S, the question is like, can I get to this one? The answer happens to be yes, but can you get to this one? The answer is actually no, right? Because you can only flap up so high. And the key to that is, if you consider this the x-axis and this the y-axis, is because you're moving once each step, the highest you could ever go from this position to this wall on this x-axis is the distance along the x-axis. So if this is 7, the highest you could ever go is 7, right? So 1 2, I guess it's 0, right? Right here, this is the highest you could ever get, right? And then because on this one, here's where the gaps is, the distance from here to here is what, 1 2 3 4 5. So you could, starting here, you could never go more than 5 below this one, right? 1 2 5. So like this is the actual minimum from this point. You couldn't ever get to there from here. And so that would be like your neighbors function. I think the problem though in part 3 you run into is the number of neighbors can be quite huge, right? So you imagine you can cross this like gap, but there's like a each of these represent like I don't know, 10,000 nodes. From this position, maybe you can only reach 4,000 of them, but that's quite a huge branch, right? And when the number's quite large and the number of walls are quite large, that it makes that quite difficult, I guess is what I would say. Especially if you're doing it one position at a time, right? It's like if you say my neighbor for this one is either here or here, right? That would be the neighbor for this single position. Now you've got to go really far. So I started thinking, when I realized, oh, the distance right here, along the x-axis is actually equal to the distance that you can go up, like the maximum value you can go up and down. And so that allows you to do some very, very cool things, right? For example, we now know, like, between any two distances, like the reachable area it kind of creates like a little ray, or not a ray, like a segment of an angle segment. There's probably some math term that I'm missing. And so this one from here to here is like this ray right here, but then it also goes like up here. It's not a ray. It's like an angle. Looks like this. Goes like this. So you could only, from this position, you could only ever reach these ones. And so you really just need to know which one of them overlap right here, right? And if you keep like a running list of from my current position to my next position, which ones overlap, you just kind of keep track of that list of like which ones overlap. And once you get done, you know the best you can do is the smallest overlap, which is right here, which is like, and that's exactly how you solve it. The one key thing that you have to do, like the thing is like you could get to this position or this position or potentially this position using the same number of ups. So you kind of have to do some weird math, and I might try and show it to you. Well, here's kind of what it looks like, just to show you. I had AI help me draw this diagram. Like if you think what's happening, again, you kind of cast this area of reachable zones, and now you know, oh, the only reachable zones from here are actually right here. So now I keep track of that list, and that will overlap from here, and that comes down here. And notice, like, even though I can't reach from here, imagine I could reach to some of these would overlap. And so I just need to make sure I'm maintaining like a single list for all the positions. That becomes slightly harder in part 2 or 3 because there's multiple openings, and that's what this is showing, right? But this is the generalized idea, right? Is I know that at any point I know from this position, the only reachable places that from this position, the only reachable ones are like the intersection of this blue line with the openings of this wall. And the hatched areas is an interesting one. So what are these little hatched areas like right here represent? The way that the thing to think about is if I'm starting at this position, not all of these values actually work. So like these values right here don't actually work. And why do I say that? It's because you have to think about what's happening as you're traveling. You always are going up or down. And so you would never actually draw, you could never just like go up and stay on this line forever. You have to go up or down. And so you're always going up, down, up, down, up, down, up, down, up, down, up, down, or up, 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 down, 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 up, 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 up. You're always moving, I guess is the way to say it. You're never maintaining a steady state. And that means you have to maintain the same like parity of odd even with the grid, right? Or with where you started. So if you started here in an odd, I actually did that the wrong way, because so like if you start here and you know you're an even, the only place that you can potentially go is an odd. And it's just because like this row, this number right here can't have the same parity as this one, right? This is 0, so it's even. So its next one has to be odd, right? And you can think about that if you look on the number line. So this one has to be, if we start at 0, the next one has to be odd. So I have to either be up here or down here. Now I have to be even, right, on this number 2. So if I start at 0 and go to 7, I know I actually have to be in a different hatch mark. And that's what this like little hatched area is it's showing like the odds versus the evens. I know I have to, like if I start here and it's odd right here, I know I have to finish in an even area. I hope that makes sense because you're moving up and down. And so with like that information, you're actually able to do some like fairly cool stuff. And so that's let's show you what it looks like in the code. how do I start? I create some openings. So this is just parsing the input. I just parse the input, right? And so I get the distance. So this is the distance from the beginning. The start, like where does the opening start? And then the size, like how big is the opening? Those are the three things that they give you. So I call this parse function. And then I create a wall structure. And this is mostly interesting in part 3 because the walls actually like overlap, right? Or sorry, the openings can overlap, right? The input was actually very helpful because it was sorted. So like if you look and there's any overlaps, like it's always sorted in order. And so that made it really nice for like trying to solve the puzzle. You don't have to pre-sort it, although you could have sorted it, I guess, to get around it. But I create a wall structure and that tells me the distance and any of the gaps, which are just, you know, the gaps that are associated with that wall, right? The start to the size. But I now treat it as this range object, which you'll see below. And the idea is I can do like this iter fold to like group up all the walls. And again, this doesn't apply in part 1 because there's not multiple gaps per wall, but for part 2 and part 3 it does. So how do we do that then? How do we merge them? Well, for me, I thought this was a cool use of fold, right? Is I can keep a list of the walls that I'm working on, excuse me, and excuse me, that and or the walls that I've had, and it may be empty, right? But I will have I'll have some in there, and and then I just create my gap from that current one. So this is my range function, which you'll see in a second. But I start at the start, and then I go from the start plus the opening size minus 1. So this gives me my range of where the gap is. And then I can use this cool thing called last mute. So this says, get me the last record in my vec. The first time it will be empty, so it will be none. And so then I push a new wall to the end. Otherwise, if I get the last, it's mutable. And so I have some wall now. And I just ask myself, is my wall distance equal to the opening distance? And if it is, I can just add my gap to that wall. If it's not, then it's going to fall through here and create a new wall. So I thought this was kind of a cool, neat way. This one I figured out after I'd solved it. I spent some time, you know, like I usually do, spent some time refactoring the code and making it look cleaner, making it look more readable. But I thought this was kind of a fun thing to show. I don't know how it compares to like readability, but I thought it was a cool idea. Again, the gist of like how that works is you know, you imagine you have like one, two, two, three, four, four, or whatever. As you're going through the list, you'll create one wall, and it will do, you know, it'll say, oh, okay, we have a wall with one, and then you'll see this one, oh, it's the same distance, so we'll create the other one. Now we see a 2, and it'll say, okay, create a new wall with 2. Then we put a 2 in there. Now we see a 3, so we put a 3. Then we see a 4, so we put a 4, and then the other 4. And so this is what you end up getting. So you start with this, and you end up with this. You end up with walls and all of their gaps. And again, that's mostly useful for part 2 and 3, where you have the gaps. So here's the range operator. Basically, we have a start and end. I kind of wonder how much of this we could do with the actual range struct in the standard library. The reason I say that is because, excuse me, you can obviously do things like, is it empty and stuff like that, or the expand wouldn't be too hard, right? As you can say, oh, you know, reduce my start by amount and reduce my end by some amount. And then obviously you could iter over it. This is the reachable function though, which is like the interesting part of it. And I don't know that there's an easy, I suppose you could just use the standard library range and then just call reachable with your 2 ranges. So I'll show you all that code in a second. But now imagine we've got a wall, and so that wall contains a list of gaps in the wall. So that's the range of gaps in the wall and the distance to it. And I'm going to skip over this range thing really quick. I realize now like it's probably not very useful. But well, actually maybe we should do this. I think I did it in this order for a specific reason. We want to do a couple functions on this range operator besides just like is it empty or create a new one. We want to know if it intersects with another range. And the easiest way to do this is to get, you know, the max of the two values and the min of the two values, and that will tell you like how much of it overlaps, if any at all. And like, what is this doing? Essentially, if you have like a range like this and then another range like this, if you get like the max of these two values and then the min of these two, it's gonna like produce this range right here, which is the overlap, right? So this right here is the overlap. And like that's what we're going for, is we want to find that range. And this is just, if you've done this before, you know, you do a max of the starts and a min of the end. And that gives you, so that will give you your new range. Because we're using eye sizes, we'll know if it's empty, that is, it doesn't intersect, if the start is greater than the end, right? So if you had some value like, you know, imagine there were two arrays or two ranges, one was like this, one was like this, right? The values you'd get were, or the range you'd get was this to this. And because those don't like overlap, you know, you haven't they don't intersect at all. The expand function you'll see me use is because, and it has to do with like where your current position is and like how you want to expand it out. So like in this graph, you imagine you want to take this, like, and this is not, it's actually this chunk right here, right? You want it, like, you want to take this chunk and expand it to this, because from this distance, that's the new range that you want to interact with. So that's what that expand is for. That makes sense. Maybe I can draw that. So this is the expand. You start with this range and you expand to this range. So this is the expand. Then we have an iter. Again, this is a lot just like a range iter. So there you go. Now the reachable, I do want to do this first. So let's talk about the reachable. What this is saying is, can you tell me which nodes or which points on the next item are, or on the net or on a next range, are visible or can be hit from where I'm currently at. So I have myself my own range, and I have some opening, right? And then I have where I'm at and where the next one is at. And these two are here just to help me do like some math. Right here, right here, right here, these type of things, right? So I do a little bit of math. I'll go over it for a second. But how does that work? Well, if you think about what I'm going to do, is I'm going to have this range and I'm going to have this block right here, right? So this is my, this part right here is my cur. And then like this part right here is my next. I didn't, but this is my next. Do I call them cur and next, right? Yeah. So, or I guess this is my opening and my next, right? And this is my cur and my cur range. Myself. It actually ends up being this part right here, right? Because we expand it. So I'll show you what that does. So what do we get? Now we want to find what that intersection is. So we expand ourself by dist. That's going to expand us. That's going to call this expand and make us like this block right here. And then we're going to say intersect us with the given opening. So that's this block right here. So the net effect of that is we now have like this range right here that we're working. Like this is the range. Hopefully that makes sense. So we have that little block that is our intersect range. And so now we just have to say what is a min and what is the min and max valid heights from that range, right? So how do we go through there? And what do I mean by that is this is the odd even part of it, right? So not all of them are valid, in fact, and but we want to find the minimum one that's valid, and we also want to find the maximum one that's valid. So we do know there's this intersection, but the way to think about it is like the top and the bottom of them. Like if I were to zoom this thing in down here, we now have this range, say from 50 to 100. It's possible that like 100's not valid, so like maybe it's only 99 is valid and 51 is valid. So like this is the actual valid range, right? We don't want to include the values that are not, but also the ones that are like not valid are in here are the ones in the hatched areas, and like that's kind of the thing. I'll show you that in a second, but the idea is we're going to start for the minimum one, we're going to start at the beginning of the range, and we're going to eliminate any of them that aren't valid, if that makes sense. Any of them that aren't valid, like, and so that's where this is multiple of 2 comes in. So where the next minus y, so y is this current value, like the 50, for example. So if that minus y is not a multiple of 2, then we know it's not valid. We don't want to include that. But now, given that, we can now create a range, and we're going to find the first range. We're going to find intersections of that range, and we're going to find the first one that's not empty and is a correct multiple. I hope that makes sense. So these y's are going to help us. Actually, do I need to do this now? Was I overthinking this? I'm gonna try something quick. Y minus this y plus, right? You do have to do this. So what could also make these numbers invalid? Like if this distance, remember, you know you're going to travel this far, so you know you only have this much to work with. So even though like these intersect, right? There may only be like some of these that are valid. And now that I'm thinking about it, doesn't this solve that? Like if I do this, yeah, I don't actually think I have to do this, because now that I think about it, this fixes it. This part fixes that, right? The expand fixes it. I may have overcomplicated this part. Rev next multiple 2. So yeah, I think I did. My thinking at the time was this is the right problem. Yeah, I am overthinking it. Okay, that makes it even simpler. Okay. Yeah, okay, it is much simpler. And again, like my thinking was is like even though you might find, and this may have been just me iterating through the code as I was solving it, my thinking I think at the time was, okay, now I've got this range. I need to like there may be some that aren't reachable from this position, but it occurs to me now that all of them would be reachable because I already expanded and intersected these two. So now I only need to like either move up or down based on the ones that are the bolt. So that does make this much cleaner, right? So again, maybe to reiterate then, how do you determine what's reachable from a current range to a new range is you expand it by the distance you're going. I actually can get rid of this next curve. Yeah. So we expand it by the distance between the two, and then we say what does that expansion intersect with? And then we may just have to move the min and the max up and down. And I do think you still have to do this option. And the reason I say that is because it's possible that if you like, maybe the gap is only 1, but it's not equal, or sorry, the parity's not right, then it like closes the gap. And that one's, you couldn't actually ever get there. Like, what do I mean by that is like, assume the gap was like this, it was only 1, and you're right here at this position. Well, you either have to flap up into the wall or flap down into the wall. You have no choice, right? So that means that this gap, actually, there isn't actually a range there. So you have to take it. Okay, so just to recap, what have we done now? We now can say from any gap or from any position in the gap, we're actually going to start at a range right here. We can figure out how much of this section is reachable, how much of this section is reachable, you know, and like how much of this section is reachable, right? And we're just going like from here to here, from here to here, and then from here to here again. Maybe only like this part is reachable. I've written over this so much that it's probably not helpful. But the idea is we can now show which parts are reachable and which parts aren't. So I'm going to create a reachables struct, which I can then iterate through and say get all the reachables from my current position, and then calculate all the reachables from the gaps in the next position. And this is where you could do part 1 just with this single one, right? With this single one. Which I think I did when I was solving it. I actually don't remember. Yeah, I don't remember how I did it now because I've done so many iterating through it, and I've also done day 20, which is like fresh on my mind. But I think what I did was you could really just solve part 1 with this, but part 2 and part 3 you need you have multiple of them, so you need to keep like a list of ranges as you're moving from one to the next, and you kind of have to like find those, merge them together, and do that stuff. So I'll show you what that means. And all that is to say is, now that you can do it from one to the other, when you have multiple walls like this, like imagine your actual position was right here and like these were reachable and these were reachable, your first like reachables struct would just contain this point, but then your second one would contain this range right here and this range right here. That makes sense. And then that affects what happens here, right? Because imagine there's like 3 gaps right here instead of just this one. Well, you now know that, like, you know, maybe this one can reach all of this, and this one can reach all of this, and this one can reach, you know, some amount of this or whatever, right? So you kind of have to figure that out. And you're just tracking these ranges. And again, once you've tracked all the ranges, you can once you get to the last one, you now know what all the ranges are, and you just use the smallest range. Bob your uncle. So that's what this reachable struct is. And what does it say? Given my current position, which the default is my 0, 0, so there's only one range and it's at that single point. That's like the quote unquote start. Go find, I can call next on it, given the next wall, and it will go through all of them and find the, you know, how many ranges overlap and how many of them. And the way you do that, or at least the way I did it, was with a Cartesian product, right? We've done this before, I think. So we take my ranges and do a Cartesian product over the gaps in the next wall, and then we just and then for each of those, right, that's gonna, you know, say there's like 2 on one side and 3 on the other. That means in total there'll be like 6 of these iterations we'll run through. But what we'll do then is for each of them we'll have our previous range and our opening in the new wall, and we'll say for the previous range, how many are reachable from the opening. So this is where we call our reachable. That's this right here. And we're going to filter, right? Because it may return some, but it may also return none. It may say none or are reachable, right? So for example, up here, something down here would be unreachable. So there would just be nothing there. You skip it. And then we're just going to fold them together based on their ranges, right? So we're keeping these in like sorted order because we're going from the bottom to the top, like y equals 0 to y equals n, like the maximum value. So they're always staying sorted. So we can actually do a similar thing. This filter map is going to give us a bunch of ranges, and we can now merge the ranges similar to how we did up here with the layout, with the opening. I couldn't reuse the code. I suppose there might be a way to reuse this, but I think there might now that at first I couldn't do it, but we may actually be able to. It's slightly different because the input expects there to be no gaps, but there could be some gaps, right? And so like what's happening here is we say again, we say, hey, get a mutable reference to our last value. And if there's not one there, or, you know, or the ranges don't overlap, then we just put our range in there. Otherwise, we're going to take the last range and we're going to like update it with the ends, if that makes sense. So the idea here is if there's ranges that overlap, we're not going to do an intersection. We're going to do like a union of them. Like this has the effect of if one range comes through looking like this, and then another range, and then the next range comes through looking like this, well, the actual range here could actually just be this to this, right? So imagine this is, I don't know, 7, this is 3, and this is 5, and this is 1. Well, the actual range between these is 1 to 7. And so we can do this merge, and it just helps with segmentation, right? I don't know if this would technically be an issue because I'm able to solve it in like microseconds, but there's a potential that if you like keep all these ranges, it starts to get like very segmented and you get a bunch of them. And we've had problems like this before where segmentation becomes an issue and you'd much rather like merge them. And so that's what I did, is I merged. And so that's what this has the effect. Maybe I could just add that right here. So like that's essentially what we're doing here. We just filter by reachability. This is going to give us that reachable range, and then we can fold them and merge the ranges that over. Okay, so the last thing you do, now that you've done all that, presumably here at the end somewhere, you have a list of ranges that are like quote unquote valid. And it may be like this is a range. I mean, we'll ignore, this is a very simple example to illustrate it. But imagine there's a range up here and a range up here. So what is the minimum number of flaps you have to do? There's actually some math to this, and the way to think about it is, remember the distance you're going along the x-axis, it has to be you can't do any more or less like ups and downs than you could. So the way to do I still have this the flaps plus the downs is equal to the y, right? The y-axis. That your ups and downs is the number of flaps plus the number of downs. So like, oh no, minus flaps minus down. It took me a minute to figure this out, but I did figure it out. And then flaps plus downs equals x. I'm pretty sure these are the two. Here are the equations. Let me do them right here. To get the y-axis, right? So this is your up downs. It's going to be y equals the number of flaps that you do minus the number of downs, you go. So this is if you don't press anything, you go. You're always going up or down. So you know your y-axis is the flaps plus the downs. And your vertical movement, your x-axis, is going to be the flaps plus the downs. Okay? So this is a system of equations. There's two of them. So you can actually solve this, right? Like a normal system of equations, I guess. Right? So if we move what we want to know is what is like the minimum number of flaps. So I think we actually want to leave f as it is and like solve for d over here. So we'll say for this equation, we can say d equal to x, nope, plus f, nope, minus. D is equal to x. Yep. So we set d equal to x minus f. We put it in here. So our new equation is y is equal to f minus x f. So that has the plus. So now we get 2f equal to 2f f. I don't think that's right. Is it? Did I do something wrong there? Nope, I did. Okay, there it is. So this is the equation that will get you your the total number of flaps, right? So the number of flaps is the x plus the y over 2. So we know what the x is, right? It's the last distance. So that's this right here. So the question is like, what is the y? Well, we can just pick like the very first range, right? So we put the smallest y value that's in the reachable range. And because we've kind of kept it in sorted order, we now just say, so it's the first range and the start of that range. We add those two together, divide by 2, and that gets us our reachable range. I hope I did that math right. Part of it feels wrong. I think I did mess up something up. I don't want to delve on this too much because it's like silly math. I also hope I didn't do this wrong. I just lucked in the right answer. But x f y f minus distribute. Oh yeah, so it's f minus x plus f equals. So now you get x plus y to f. Okay, there we go. I did do it right. Got it. And that's the solution. So that's how you solve it. So how do you solve part 1, part 2, and part 3? Well, we just we parse our input to get our openings, our gaps, and then we create our walls from that. So we create all of our walls and we just iterate through each of the walls, and we start with an empty one, the blank one at the start position at the 0 0, and just for each of them we say, hey, get me the next reachables from that wall. So and we just do that over and over and over again until we get to the last one. And once we get to the last one, we say, okay, give me the solution to that last one. Boom, Bob's your uncle. Solved. I don't know why I keep saying Bob's your uncle. I don't even know if that's a cool phrase. But that's how you solve all three parts. And so it turns out, like, in the end, I mean, I realize I did a lot of math, but if you have 2 hours of driving to think about it, I don't think I'd figured this reachables part out, so I did have to solve that after I got. But it wasn't too hard because the idea was still the same. Is like you just had to kind of figure out this part of it, like what is reachable from each thing. This part is not actually that hard, right? Because if you think about what you're doing, is you're just saying, okay, well, I'm just taking the list of gaps that I currently have with the list of gaps or the list of like valid ranges from the wall that I am at right now that I know I can get to, and I just merge that with the list of ranges in the next one, right? And so you do the expansion, you check the overlap, you like adjust the min and max based on whether they're odd even parities, and then now you have a new set and you just do that over and over again. And so that's the I think this I did do this between part 1 and part 2 would be my guess. I don't know why you'd try and do this without, so I don't think. But there you go. That's the 3 parts solved and done. So let's look at progress. Oh, it's gonna show all 20 because I done day 20. Yeah, I just finished it. Let's see what we got though. I know I get stacked. Yeah, we're getting like scales. Boom. Oh, we got a metal intake. Look at that, we did it. Okay, well, you'll see how we did it in Quest 20. Let's look at 19. See. Yeah, again, an hour and 10 minutes. Almost certainly it didn't take that long. Because I had like 2 hours of driving. So this does feel like it's, at least from my perspective, it's more like a 2 to 3 hour problem. So the ability to like think about it for a while kind of got me there. Yeah, I do think there's like a 20-minute gap here, around 11, 15-minute gap. 7 plus 6, yeah, whatever, 15 to 20, yeah. That probably explains me having to say, oh, I have to like, now I have multiple walls, and so there's multiple reachables. Now so I create the reachable struct in that 15. And then yeah, from part 9 to 10, because you'd solve the reachables, and I happened to have done it the right way. I think this gap would have been much different if like I had like it. I think in part 1 you could solve it in a much less naive way, or much more like you could actually do like a BFS of all the values. And I suspect it wouldn't be possible in part 3, but we'll see. Wait and see how it's all. But yeah, my numbers don't look very good. So yeah, yeah. So let's go look at some solution. Oh, let's see how fast people solved it so I can make myself bad. 19. 10 minutes. 30 minutes. I think Hyperneutrino was one of the ones that won the whole day, or the whole 10th as well. Yeah, these are really good. Where would I have even placed? I guess it wouldn't have been that bad. Somewhere in like 6. Sifco is someone that I think also won. Like got in the top 5 or whatever. being able to solve it in about the time it took them, that's not shabby. This one I do feel was like very math heavy. I don't think it was like, you know, you're dealing with hypercubes or whatever difficult, but you know, was it actually math heavy? I don't think it was actually, now that I take it back. I mean, you're just dealing with range. It's kind of I think the way that maybe the way to generalize the solution was, at least the solution that I gave was, it was like a dynamic programming where you're just basically like, okay, just work on this wall to the next wall and then figure out like the ranges that overlap from those two, and then now move on from that, take that wall and then work on the next one, right? um let's go look on Reddit, see how what, oh, we got lots of comments. uh True. The way that I thought about it was, because if the next one ends on an even spot, like the next one would be odd. I think the even odd thing, the parity thing, is important because it reduces your ranges. Like there's some ranges that are just not valid. You could never get there. And so you have to account for those, right? Like you could never go to a specific spot, a certain spot, if that makes sense. If a position XY is reachable, the number of wing flaps is predetermined regardless of the flight. Yeah, that's right. Again, like the X and Y. Oh, here we go. Yeah, they came up with the same thing. You can, like, again, you can calculate the number of flaps to get to any position this way, right? And I think that was the key to it, is like you kind of just got to figure out those ranges, and then you can do the math to do this, and then it becomes like an absurdly simple thing. So I imagine their solution is similar to mine. Gapping, yep, do the gaps, figure out intersections. Start at this one, you get your next. Yeah. So I tried to make mine more readable, but this is the gist of solving it. And this type of thing works for part 1, 2, and 3, right? Like the difference between them is nothing, and so you can solve all three of them. Same problem. Okay. Yep. Very good. Step increase automatic. Okay. It looks like a lot of people came to the same. Okay, we've kind of followed him a lot, or them a lot. Man eating 8, 7th place, I think, is really cool. Working out the formula, this paid off during part 2, 3. Yeah, this was the thing, right? Is I think I would be interested. I mean, we'll look through some more, but there's a potential for part 1 and part 2 to have been solved with like a pathfinding algorithm. Because again, if you know how to do like a BFS or a Dijkstra's, the only thing you have to ask yourself is like, what is my start state, what is my end state, and then what are my neighbors? And so like you can think those through for this problem, and I think you could solve it with a Dijkstra. But again, because I might have actually done that and really hated myself for part 3 and spent some time figuring it out. But because I had enough time to think about it, you could kind of look at the problem and come to the solution. So let's look at what they did. Solve, solve, solve. Yep. Again, what the? Is it even simpler than that? Did I even overcomplicate it? Like, what are they saying here? That's absurd. Like I had done this to kind of like figure it out, like what the reachable. I knew like the end was this, but I kind of assumed like some like say there was like something down here, like something down in this area right here, but it wasn't actually reachable. Like this would be the only thing. I figured you'd have to do more logic than that, but this seems to suggest it's not. It's like you literally just do a div seal for each of them and find the max of it. That's actually, this is where like my math knowledge. Maybe this has to do with the problem itself. Yeah. So like what they're saying is the input is not adversarial, meaning like it was intentional that like you could always get to the bottom one. And so that's how this solution worked. Got him to 7. But if you can figure it out and it solves it, that's actually really cool. So congratulations, number 7. That's awesome. I don't even think like what was my best rank. It was always in like the 6 to 100. 180, 6, 31. That was probably my best. Yeah, I don't think I'll ever do better than that because I am slow. I am not fast. That reference still applicable? Does anyone know where that's from? Total panic as I was struggling with part 1. I finally got everything. We're fine for all part 3 run. 45 seconds. 45. So are they doing some kind of graph? This can't be 40. Oh, it can because the ranges are large. So because this range is really large. Okay, but you know what? If you solve it, that's cool. For each X with a wall. I think if you actually use Dijkstra on this, it's the last part's not going to be. But that's still cool that you're able to solve it for all 3 parts. Okay, if you can actually solve part 3 in Dijkstra, let's look at what their neighbors function. Start at 0, 0. Next, open. Okay, is that actually true? Does it? So maybe it actually turns out to be that odds never work. Is it because all of them are even? That's true. I think what it's saying is, and maybe I'm getting this wrong. Like what it means is like because you're going up and down, the parity always goes you're on an even number, then you're on an odd, then you're on an even, then you're on an odd, then you're on an even, then you're on an odd. And so like the to get to a position on a wall, you may be odd or even, but it you'll have to have maintained that parity. And like I think that's what the code is his code is doing, but you can see like the difference of these have to be a multiple of 2. And that is to say, again, if it's 2 odds, you would get an even. If it's an even and an odd, you would get an odd, right? And so you'd want to exclude them. Yeah, I don't know what this means. Every odd is impossible. Like, am I just, maybe someone can help me understand this, what I'm missing. But like, you can definitely get to 1 and 1, right? But from 1 and 1, you can't get to another odd. You can only get to these evens right here, right? And then from those, you can only get to these right here, right? So like, it kind of, I don't know, the way to think about it is it like triangles out like this. So like, from this node, like if you're doing your pathfinding, from this one you have to presume you're going here. Oh, maybe that's what they're doing. Like, from this one, you know it's going here. So when you are doing a neighbors function, if you have these 3, you know your neighbors are these 4 right here. So that's why the quote unquote step function works in that way. Okay. Okay, I think I understand why they're doing it. So that makes sense. Because when you're doing a Dicers, you're saying like, what are my neighbors, and you know your neighbor's not going to be like directly across from you, or is it going to be like, that makes, okay. Yeah, I did have this, although I did see this, and so I updated. I have a tool. I don't, I mean, you can kind of see the stuff right here. I guess you can't see that on my mouse, but down below my debug, and then up to the right, I have like my, or up to the right is my debug, and down to below is my summary. I have like little new shell scripts that help me like do functions to like pull the stuff. I happen to see that it changed, so that was a problem. Yeah, once you do the gap rangeability, it doesn't take any time to solve. Let's see. Not now. Bummer. Okay. I had this. I promise I've had this happen several times. It is the one nice thing about Advent to code is the input doesn't change, or if it does, it's all like, your first input was this number, and now your second input is now solved. And so like, you didn't actually really use your input as a text file, but most of the time the input doesn't change. It's just something else that changes that makes it more interesting. I kind of like that better than the way everybody codes does it. Although I can see pros and cons to either side, right? You have, because if you only have one input, you have to design your puzzle in such a way that the build up to the final solution like uh, works for all 3 of them. Whereas you can do multiple inputs, you can start with something small, then go to something absurdly large. Um, 've had hard days too, so don't feel bad if you're reading this or watching this. Sometimes you just have bad days. It doesn't work. Again, we don't talk about Quest 10. Yeah, this seems like, why would it take so long? Or maybe it's just, so there's been some times, I don't know how this works in C#, but like in Rust, if you aren't careful, you can suddenly find that you're cloning vectors of large arrays. And I think I told you this, right? In one of my days, I inadvertently created a hash set that was like 128 gigs, took up all of my memory. Not happy. Okay, it looks like we got some really good solutions. Yeah, you could definitely get down, upgraded to pairwise minimal distance between. So, okay, this is, it sounds like this is a smarter way of saying what I did, but I suspect this is the same. 24 minutes per second. Dijkstra using coordinate compression. Oh, that is a cool thing. We had talked about coordinate compression in other problems. You could probably do coordinate compression on part 3 and solve it. So if you've done Dijkstra on part 1 and part 2, and suddenly part 3 is too big, you compress the values. Boom. That's actually cool. That's a cool idea. Okay, I hadn't thought of that. Okay, I think that was an awesome day. Very fun. So lots of cool stuff from this one. 1 day left. You'll see the video coming up soon. I think that's it. This has been a lot of fun. Let me know what you did, how you solved it, what was going on. Figured out. So what happens is like I have contention for the cargo lock, and sometimes there you go. Thanks everybody. We'll talk to you next time. Bye.